Hey everybody, good morning. This is Mr. Ainsworth, and we're going to get into a review over the first six sections here in discrete or modern math. And so, have your review out. I would also have all your notes out from 1 through 6 so you can access those if you need to. And I would have a red pen, a highlighter, all kinds of stuff to get ready to do the best job you can to get ready for your test over the first six sessions. All right, so let's get right to it. Well, in the first few graphs here, we got to explain why. Okay, the each of the following graphs has an Euler circuit, path, or neither. So you have three choices here. You can say that it's an Euler circuit, or an Euler path, or how about none exists, okay? Let's write that down. So a path doesn't exist, so they don't exist due to Euler's theorem. So we'll talk about reason why, okay? And what we want to do is provide the degree of each vertex in red. We want to do that in red on the graph so we can easily see it and identify it, because that is what we're going to look at to base our opinion, okay? We're going to use Euler's theorems here. So let's go for it here. So the first vertex, we have one, two, three edges coming into this vertex, so it's degree 3. We have one, two, three, four edges coming into this vertex, so it's degree 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. It's a counting exercise. Count the edges coming into the vertex and it tells you the degree. 1, 2, 3, 4. All right, so notice I have two odd degrees. So because of that, right there, Euler theorem says, hey, this doesn't have a circuit. It has a path from this vertex to this vertex over here. These are odd degrees, right? Everything else is even. All right, so the first one here, graph A, is a circuit. First of all, excuse me, why did I say circuit? Path. Come on, Ainsworth. It's early in the morning. It's 6:30 in the morning. I said it correctly here. It's a path. Come on. It's a path, and the reason why is because it has exactly two odd vertices. Okay, two odd vertices. All right, exactly two odd vertices indicates its path, as opposed to a circuit. Okay, which has no odd vertices; they're all even. All right, so you're going to look at the degrees. All right, over here, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. They're so far they're even. Okay, 1, 2, 3, 4. 1, 2, 3, 4. Okay, they're all even. All right, so that tells me that on this one here we have a circuit. So let's indicate that. All right, vertices are all even. Come on. Vertices are all even. All right, there's the theorem on that. The keyword is even. If the vertices are all even, which means you have zero odd vertices, okay, you have a circuit. Okay. Next one, we have 2. 1, 2, 3, 4, 5. We got 5 here. 1, 2, 3, 4, 5. Another 5. 1, 2. And up here, 1, 2, 3, 4, 5. Ooh, we got a lot of fives. Okay, already I can see, because I have more than two odd vertices, no path nor circuit exists. Okay, but I'm going to continue. 1, 2, 3, 4, 5, 6. We got 6 here. Another 6 here. 1, 2, 3, 4, 5. 5 here. 1, 2, 3, 4, 5. 5. Got 6, 6. 1, 2, 3, 4, 5. 5 here. 2 here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 2. So we have too many odd vertices. We have more than two odd vertices, so neither here. Okay, neither. Why? More than two odd vertices. More. Oops. Okay, than two odd verts. More than two. Okay, it has a lot. I mean, talking a lot here. Look at that. Got a lot of problems here on this one here. Okay, when you have more than two odd vertices, you got a problem. You can't find a path nor a circuit. So remember that. It's an Euler theorem, all right, from section 5. Okay, so now once you know it exists, you got to find it. Okay, so on this one here, you're going to decide whether it has either an Euler path or a circuit, one of the two. You have to number the edges. Look at that, read the directions, and you have to put arrows in the order as they are traveled. Okay, so the first thing we do is we decide whether we have a path or circuit. So we look at the degrees. So 1, 2, 3, 4, 5. Ooh, this is odd. This is an odd vertex, so I already know it has a path and not a circuit. So this is a path, first of all. And the reason why is because it has at least one odd vertex. If I have more than two, then I don't even have a path, okay? But so I'm looking for another odd one because I'm going to start at one, end at the other one. So I have 1, 2, 3, 4, that's even. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, okay. Where is 1, 2, 3, 4? Ooh, this is another odd one right here. Okay, so 2, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 1, 2. So I have two odd vertices in red. Okay, so what I'm going to do is I'm going to start here. I'm going to end here. Okay, that's what I'm going to do in a minute. So I have two odd vertices, exactly two odd vertices. Tells me that I have a path. Okay, so here we go. I'm going to move around there. Now, there are more than one path possible, so remember that. So I'm going to go to the left here. 1, 2, all right, 3. I'm just going to move around here. 4. Excuse me, that should be a 4 right there. Let me switch that. We got 4, 5, 6, 7. So I'm going to cover the lower half here. 8, 9. Now I'm going to move up. 10. All right, now I'm going to move around the upper part of the graph here. 11. Around here is 12. All right, 13. Moving around. I'm going to go around the loop here. 14 here. Come back down here. 15. Around the loop. 16. 17. And then back up. 18. All right, and that shows you my path. All right, I start and end at an odd vertex. Remember that for paths. But first you look at the degrees. So look at the degrees first to find the odd vertices. So look at the degrees first. All right, to find the odd vertices. Okay, so remember that. On this one here, what do we have? So we have 1, 2, 3, 4, 1, 2, 3, 4, 4, 2, 1, 2, 3, 4, 5, 5, 1, 2, 3, 4, 5, 6, 1, 2, 1, 2, 3, 4, 5, 6. They're all even so far. So they're all even. So we have a circuit here. Why? Because all even vertices. So all even vertices indicates a circuit. All right, so what I'm going to do is I'm going to pick a start and an ending point. So I'm going to start here, and then I'm going to end here. Why? Because it's a circuit, and a circuit you have to start and end at the same place. So I'm going to go down here, 1, 2. I'm going to travel around 3 here, back up here, 4, across here, 5. I'm going to go. So I'm going to do the upper half, 6, and then 7, and then come down here, 8, 9. No, I'm going to cut across. I'm going to cut across here. So 9 across here, and then I'm going to come back down. 10, and then I'm going to go back up again here. 11, 12, 13. Let's see here. I'm going to go back up and then back down. So right here, 14, and then back down 15, 16, 17, 18, 19, and then back up 20. There we go. So 20 edges in all. 20 edges in all. Okay. And back up to the where I started. All right. And there you go. That's a circuit. Now, if you couldn't do that like I did by eyeballing it, well, then what you do is if you need to, if needed, okay, use Florey's algorithm and go to the side and copy this off to the side and delete an edge as you go. So that's if you need to, okay? Use Florey's algorithm. That's if you need to, okay? All right, I went over that in section 6. Now let's review some other basic concepts here, which we already went through, but let's do them again. All right, so the first one here We want to label the degree next to each vertex and state whether it has a circuit or a path and state why. Okay. All right. So degree 2 here. 1, 2. This one has 1, 2, 3. Degree 3. 1, 2, 3. 4. Degree 4. Degree 2. Degree 1. Degree 2. 2. 4. 1. 3. 3. 3. 2. 2. All right. So in this one here, we have 1, 2, 3, 4. We have 4 odd vertices. 4 odd vertices. Okay. Euler path or circuit? Neither. Okay. More than 2 odd vertices. More than 2 odd vertices. Okay, so it has neither, right? So this right here, we have 6 odds. The question is, how many odd vertices do you have? You either have 2, 0, 0, 2, 4, 6. You have an even number of odd vertices. The question is, how many do you have? Okay, so what I did is I labeled the degrees in red, all right? And either it has an Euler circuit or a path or neither, all right? And then, of course, you have to state why, all right? Here in this case, we have 4 odd vertices, so it doesn't have either one of them. All right, so on this one right here, degree 1 and 1, degree 0, degree 1, 2, 3, 2, 3, 1, 2, 2, 2, 3, 1. Okay, so here it's also disconnected. So it's disconnected, so it can't have either one. You notice right here, one's isolated here. So neither again doesn't have either one. And it's disconnected, and you have way too many odd vertices. So it's disconnected, all right, and more than 2 odd vertices. So as soon as you see a disconnected graph, you're going to have a problem anyway. So right away here on this one here, I'm going to say neither because it's disconnected. Okay, but I'm also going to do the degree thing. So here we go. So 3, 2, 3, 2, 2, 2, 1, 2, 3. We got 4 here. We got 3 here. We got 4 here. 3, 4, 1, and 1. You got all kinds of problems. It's disconnected, all right, and more than 2 odd vertices. Okay, so on this one here, we got degree 1, 2, 4, 2, 3 here, 4, 4. Ooh, we're looking good so far. Okay. I missed one. So let me see what happened here. Went too fast. You can't have one odd. Oh, right here. Okay, so we have 2 odds. So we have 2 odd vertices here. 2 odds. So we have a path. We have 2 odd vertices. Okay. So it's just a vertex question. 1, 2, 3, 4, 2, 2, 3, 4, 3. Oh, we got 3 odds. Okay, no. So neither, I can already tell. More than 2 odd vertices here. So we have 4, 4, 2, 4, 4, 1, 2, 3, 4, 5. Ooh, 5, and 4 here. On this one here, we got 1, 1, 2, 3, 4, 2, 3, 3, 2, 3. We have more than 2 odd vertices here, so neither. I can already tell that. Okay, more than 2 odd vertices. Let's have 2, 3, 2, 1, 2, 3, 4, 5. Whoa, 3. We got a lot of problems on this one here. We got more than 2 odd vertices all over the place. Okay, that's how the game is played, guys. Okay, now on this one here, we want to classify the unicursal tracing as either open or closed. We have 2 choices. Okay, Now, closed means that we have a circuit. Remember that? So let's write that down. So closed uh, indicates that you have a circuit. Open means that you have a path. Okay, start and end different places. So start and end at different places. Circuit, end and start at the same place. So on this one here, we start. Come on, start. Sorry guys, start and end at same place or vertex. That's for a circuit. Okay, so here we go. Let's just go through them here. Let's see here. Let's see. That's 3, 3, 3. This is impossible. So no path. So degree 3 here. I see odd, 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 odd. So, okay, neither path, circuit, all right, exists. Too many odd vertices right here. Okay, but on this one, let's see if I get 2 here, 4, 4, there. Oh, 3 here. So this is odd and this is odd. So I'm going to start here, okay, and end here. So what can I do? So let me see. I go 1, 2, 3, 4, down here at 5, 5, 6, back up at 7, and then back down here at 8. Okay? So you can have a universal tracing if either a path or a circuit exists, because it's either open or closed. Open means that you have a path, and closed means you have a circuit. All right, so here we have 2. Looking at the degrees first. 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. And so here I have, let me see, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Where's the degree? Now I need to find another degree 3. 1, 2, 3, 4. 1, 2, 3, 4, 5. Ah, so here's degree 5. And here's degree 4. So on this one here, let me highlight these. So degree 3, 1, 2, 3, 4, 5. And this is degree 5. So I have to start here, all right, and end here. All right, we have a path. So this one was closed, all right, because we had a circuit. This one's going to be open, which means we're going to have a path. All right, so I'm just going to move around and see if I can do this here. So 1, 2, 3, 4, 5. Let's see here. 5, that's 5, 6, 7, 8. This didn't work. So 1, 2, 3, 4, 5, 6, 7, 8. Let's try it again. So we have 4 here, 5. Let me see, 5. Let me pause the video here so I can think. Okay, so let's see here. I'm gonna, instead of going across here, I'm gonna go 4 here. I'm gonna try this path. 5, then up here 6, 7, 8, 9, and then back up 10. There we go. So we started down here the lower right, and we ended up here up to the upper left. Okay. So again, you just want to play with it here. So we look at the degrees first to find the odd vertices. You have to find odd vertices for the pass. So on pass, the goal is to find odd vertices. Remember that. Let's make a little note. So 2, 1, 2, 3, 4, 1, 2, 3, 4, 4. This one has a circuit. This one's going to be closed. It has a circuit. So I can start anywhere. So let's say if I start here, I go down 1. Let's see here, 2, 3, 4, 5, 6, 7, back up here at 8, 9, and then 10 here. Okay, so start and end at the same place. That was a fairly simple one. Okay, on this one here, we've got 2, 1, 2, 3, 4, 5. So this is odd. Okay, we have an odd one here. 1, 2, 3, 4, 5. We have another odd one here. 1, 2, 3, 4, 5. We have another odd one here. So no path exists, okay? So no tracing exists, and we have another odd one here. So neither path or a circuit exists on it. So I'm not going to even try it, okay? So you look at the vertices, or you look at the degrees first and figure out how many odds you have. And if you have none, it's going to be closed and you're going to have a circuit. If you have 2 odds, you're going to start at one and end at the other one. You're going to have an open path. And then if it has more than 2 odds, well, you don't have either one. Okay? All right. Now, on this question here, number 5, are the graphs isomorphic? Explain why or why not. Well, on this one, isomorphic means they have everything's the same about them. Okay, they have the same number of vertices and they have the same edge set. So isomorphic, you have to remember the meaning of it here. Basically means that everything about them is the same. Everything about them, about the graphs, is identical. Okay, same edge set, same vertex set. All right, same edge set. Okay, everything is the same circuits, same paths, and circuits, etc. Okay, so you have to look at edge sets, same degrees. Okay, same degrees. I mean, the list goes on and on. Everything about the graphs is the same. Okay, etc. So what you want to do is look at the edge sets, and if the edge sets are the same, well, they're going to be isomorphic. Okay, so here on this one I see edge AB, so edge AB exists here and exists here, and ooh, it exists right here, it exists here and exists here. Edge, let's say CG, is here, 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 and let me see, it's here and it's here. And edge, let's say CD is here, CD is here, CD is here, CD is here, and it's here. So it's looking like they have the same edge sets. And then keep on going. DH is here, here, here. Oops, that's not DH. DH is here. Oh, it's not there either. Come on. DH. Oh yeah, I had it right the first time. DH is here and is here and it's here. So what I'm doing is I'm looking at the edge sets. All right, and then look at AE here. A is right here and here and here, here and here. And I'm going to say yes. If you keep on doing this here, guys, you're going to find out it has the same edge sets. Okay, so I'm going to say yes. The graphs, okay, all 5 of them, are isomorphic. All right, because they have the same set. All right, and that's what you got to know. Okay, everybody say isomorphic. Gotta say it a little bit louder. Okay, all right, I'll be back with you in just a moment. All right, let's continue here. Let's move down just a little bit here. We're going to get into modeling here, guys. So these next questions ask you to model this problem here with a graph, okay? And this is a new one here we haven't seen yet. It's called 11 Bridges of Madison County here. And just like the 7 bridges of Konigsberg, all right, we're going to represent the vertices as land masses, and we're going to represent the bridges as edges. So let's write that down first. So let me see. So vertices All right, going to be land masses. All right, and the bridges or the edges in this problem are going to be the bridges. The 11 bridges of Madison County in this case. So what I need to do is I'm going to say that this is a landmass up here, the right or upper region right here. There's another mass down here. And then of course you've got landmass A, which is an island, C, B, and D. These are all four islands right here. And they can all be accessed through these bridges. So what we have is we have a bridge we can get from the upper landmass to island A through Truman Bridge. We can go right through here over Lincoln Bridge to the this island here, which we call B, or we can go from right and we go over Hoover Bridge to B. Okay, we could also go from this landmass right here, cross Jefferson Bridge all the way to this landmass here. And of course, we could go all the way, take Washington Bridge and go all the way around. We could do that here too. Or we can go from island A to island C, no big deal. We can't get to island B, so there's no bridge there. We can get from C to D, of course. Okay, that's easy. Or we can get from B to D, that's easy. Or from D to this is a lower region right here, and this is the right region, the right bank or lower bank. Actually, right bank, left bank. Okay, and let me see what else. We can go from C across here, Roosevelt to the left bank, or we can take Grant Bridge and we can get to the left bank. What else can we do? That's all that I see, I think. Here, let me double check. Okay, so we're going to take that and we're going to form a graph from it. Okay? No, just like that. Right there. Oh, minus the E. Ooh, don't want to do that. Gotta love technology, man. Okay, so there you go. Didn't mean to take E. That was from the word edges. Okay, and so this right here, this is island A, and this one right here is island B, and this is D, and this is C. These are islands. This is the right bank, and this is the left bank. All right, left bank, right bank, island A, B, C, and D. So land masses here represent the vertices, and the edges represent bridges. This could be a graph which models this Madison County right here. All right, and we can talk about if it's possible to go from landmass to landmass and crossing only a bridge exactly once by looking at the degrees. Okay? Okay. That's not part of this problem. It just says model. Okay? Now here we're going to call the right bank, we're going to give that a point, represent the right bank, left bank. This vertex here represents the left bank, and then landmass D here represents, or this vertex represents that, and then the island, of course, is represented by this vertex. So we can go across here, 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 or we can go across here. So basically what we have, well, let's see here. I'll tell you what, let's just do it the quick and easy way. We have this as our model, okay? Or it could be simplified into something very, very simple here. Or 1, 2, 3, got two bridges, got a bridge here, and bridge here, okay? And this is the islands, 7 bridges of Königsberg, or today is called Kaliningrad, okay? And then we could also ask if we wanted to, if it's possible to travel along here and walk along each bridge once, traveling from landmass to landmass. Okay, on these other types here, number 7 here, we got a security guard, okay, who needs to walk in the streets here and walk on the streets of the Sunnyside neighborhood. Okay, so what do we have here? Okay, so on this one here, he's got to walk. So let's see here. So he's got to walk. Maybe he starts here. I don't know. Go to walk here, and when he walks down the street, he only has to travel once because he's a security guard. He doesn't have to travel both sides of the street, only once. So these intersections here, these vertices represent intersections. He has to walk around the park too. He's got to secure the park. okay, because he's got to secure the whole neighborhood. All right, these are all intersections here. And so he's got to walk here, 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 here. He's got to walk down all these streets. Question is how, right? He's got to walk all the way down all of these streets. Got to walk across the park, around the park. Got to walk. He's got to walk down all these streets just once because he's just patrolling the street. He's not like the mailman who has to walk on both sides of the street. He only has to walk on down the street once, okay? Because he's a patrol person. He's patrolling. Patrol. Gotta spell that right here. He's patrolling. Okay, so what we're going to do is we're going to take this, okay, and use this as our model, representing what a patrolman does as he walks around the streets, making sure it's secure. Okay, so this is our model. Okay, right here. All right, now this next one, when the male person here, it's a little bit different. Okay, in terms of the male guy, he has to walk on both sides of the street. Okay, must walk on each side of the street where there are homes. Must walk, okay, on each side of the street to deliver the mail, assuming there's mailboxes in front of every house. So it must walk on each side of the street where there are houses. There are homes to deliver the mail. All right, because he's a mail person right here, delivering the mail. So let me plot the intersections first, then we'll talk about how many sides of the street he must walk on, given this little map right here. So I'm just plotting the intersections here first. There's no houses on the other side of the school, so we don't have to go over there. We do have to go down here, though. Okay. And you don't have to go around the park because there are no houses around the park. So one pass here because there's no houses on the left. One pass here, 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 and here, and here, and here. These are single passes. Okay, not down here. Across here, these are single passes. Okay, single pass here because there are no houses above it. No houses around the park, of course. Single pass, single pass, single pass, single pass. And this is single pass too because the post office here doesn't, you're delivering from there, not to there. Okay, single pass here, single pass, and a single pass. Single pass, single pass. But here, there's houses on both sides. So he has to make two passes here, two here, two here, two here, two here. Everywhere there are houses on both sides of the street, you have two passes. So two passes here and here, here, here. Not here because post office doesn't need to be delivered to. Two passes here and here, here, here. Not here, just one pass here. Two here, two here, two here, two here, two here, two here, two right here. And that should represent the everywhere that he has to walk. Okay, assuming that he has to hit every single house that has a mailbox in front of it, like the old days. All right, so this is going to represent our model for this mailman problem, where he walks around the neighborhood delivering mail to each home, assuming there is a mailbox in front of each house. Okay? And we could use this graph right here to model the mail problem here and ask, is there an Eulerian walk or a circuit where he can get around and deliver his mail to each house along the streets? Okay? All right, number 7, the concept of a bridge. Okay, highlight the bridges in each group. Remember, bridges, if removed, makes the graph disconnected. Bridges, all right, when removed, all right, make the graph disconnected. Make the graph disconnected. All right, so because of that, FG is a bridge. All right, because if you eliminate at the edge here, G is isolated. FH a bridge because if you eliminate that, H is isolated. And then the third bridge here would be BF because if you eliminate that, then you got this other component here. All right, and you can't, removing the loop doesn't matter. The graph is still connected. I don't see any other bridges. So the bridges in this one, all right, are BF, FG, all right, and FH. Okay, over here on the second graph here, I see a bridge here. Any other edge, if eliminated or removed, doesn't make the graph disconnected. So only one bridge here. And then I see two bridges here. I see one here and one here. Okay, if I eliminate the middle edge here, that doesn't make the graph disconnected, so that's not a bridge. Okay, so I have a bridge right here, and then here, and right here. Okay, okay. All right, fun times here. Now, I put this one in here again because this one here, when we first did it, we didn't know we had to start at either KI. And the reason why is because there's an odd vertex here. So 1, 2, 3, 4, 5. This is degree 5. All right, so I is degree 5, which is odd. Degree 5, it's odd. And K is 1, 2, 3, 4, 5 as well. So this is degree 5. All right, it's odd. And so we have to start at an odd and end at an odd. Okay, everything else is even. 1, 2, 3, 4. So D is degree 4. E is degree 4. F is degree 2. 1, 2, 3, 4, 5, 6. This is degree 6. So everywhere else is an even degree. All other vertices are even degree. And because of that, we have to either start at K and end at I, or I and end at K. And you have to walk along this and use Flory's algorithm, all right, algorithm, all right, to find a path, not a circuit, a path. Okay, so you're going to start here, and you're going to end here, or vice versa. Okay, and I want you to try this on your own here. So I'm not going to show you this right here. This right here is left up to you. There's a lot of edges in here that you have to go through. If you just, let me see. If we count, well, you can count them. And just make sure that you start here and end here, start at K and end at I, or vice versa. All right, and make it all the way through, hitting each edge only once. All right, remember this is an Euler path, or an open unicursal tracing right here on this one here. So that's your goal right there, and I'll leave that up to you, and then have you guys try that. Okay, let's summarize Euler's theorems real quick. If you have 0 odd vertices, okay, well that means they're all even, okay? All right, and that means you have an Euler circuit. Okay, so you can start it in anywhere. So start and end at the same vertex. Same vertex here. If you have exactly 2 odds, the rest are even. Rest even here. That tells you have an Euler path. Okay, in that case, you start in an odd, end at the other odd. So start at an odd, end at the other odd. If you have this many odds, okay, all right, no path, okay, or circuit exists. No path or circuit exists. And this one here, if you have let me see, 1, 3, or 5 odds. Okay, we're talking about odds here. This is impossible. So you made a mistake. This is impossible. Check your work, okay? Check your work because you made a mistake. So remember that. This is really, really important. This will be a test question here. You have to tell me about this right here. So know your theorems here because that's the main essence of the chapter. So know your stuff, okay? All right, now on this right here, I want you guys to define the terms and include a picture. All right, this one right here, I want you to use your notes. Use your notes. All right, from the chapter. I'm not going to explain this. You guys can do that yourself. Chapter. And you should be able to define any of the main terms that we talked about. So go ahead and do that on your own. And on this one here, well, I'll go through this one. So what is the degree of each vertex, okay? And we'll do that in red. So degree 1, degree 2, degree 3, degree 2, degree 3, 1, 2, 3, 1, 2, 3. So this is degree 3. So we label the degrees of each vertex on the graph, find all the bridges, okay? I see a bridge here. And second one, I see a bridge here. Third one, I see a bridge here. A loop is never a bridge, okay? So bridge is AC, all right, AB, all right, and EF. Bridges are edges that, if removed, cause the graph to be disconnected. And by the way, that's on the test. I want you to be able to define that, find it, and define it. Or define it, excuse me. Okay, and let's see here. Find all circuits. Oh boy. So let me see a circuit. So let me see a circuit. B to D to E to B here. Whoa. Sorry about that. So we have a circuit from B back to B. So here's the circuit right here. So B to D, excuse me, D here. Not B, yeah, B to D to E back to B. Okay, notice that we start and stop at the same point. All right, that's one possible circuit right there. And there's another circuit F back to F. That's the shortest one here. So FF, your loop, would be your second possible circuit right here. And what is the longest path of any two vertices, and state the length? Okay, the longest path. So how about A to or C to A to B? Between any two vertices. So to A to B to D to E, F, back to F. So A. So one path between two vertices, let's say C to A. Let me start at C here. So C, A to B. To D, to E, F, all the way back to F here. Yeah, we can go back to loop around. Okay, so we went 1, 2, 1, 2, 3, 4, 5, 6. Okay, its length is 6 because there are 6 edges right here. That's from C to F. Okay, so from C, we started at C, we ended at F. That's a path, not a circuit. Length 6. All right. Okay, so there we go. That's the a lot of the main concepts from the first 6 sections here. The rest is up to you, and I just suggest you study, know your definitions, work really hard, and be your best. And I'll see you on test day. This is Ainsworth. I'm out of here.